Okay, you haven't forgotten how to determine RNS. Let's work on determining RNS on an actual molecule. Hydrogen. First of all, this is the chiral carbon, for sure, because it's connected to 4 different groups. And let's determine the RNS. Let's determine the priority of the groups first. Hydrogen is the least priority group. O comparing to, because these are carbons, right? The oxygen comparing to carbons has a higher atomic number, so it's group number 1. Now, between these two, this is a CH2 and this is a CH3. We have CH2, CH2, CH3. So what was the rule? We go further and further away from chiral carbon until we find our tiebreaker. Carbon and carbon are the same. Carbon and carbon are the same, but carbon is connected to 3 hydrogens here. Carbon is connected to 1 more carbon. This side is side 2 and this side is side 3. It's too crowded. Let me just erase these groups. So this side of the molecule is group number 3. This side is this is group 2, this is group number 3. Now, the least prior group hydrogen is already in the back. So determine the rotation from group 1 to 2 to 3. 1 to 2, 2 to 3. It is counterclockwise, so it's situation number 1. Counterclockwise, it makes it S. Let's move towards C. In compound C, there are 2 chiral carbons. This one. So the very first thing is we do is to determine the chiral carbons. This carbon and this carbon. Let's take care of the left side carbon first. Priority of the groups. Group number 4, group number 1. Between these 2 sides, carbon, 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 and now this carbon is connected to 2 oxygens, while this carbon is connected to 1 more carbon. So this is group number 2, this side of molecule, and this side of molecule is, sorry, I was talking about this carbon, so this is group number 2, for sure, and this is group number 3. Hydrogen is already in the back, so the rotation is 1 to 2 to 3, so this carbon is R. I'll show the other carbon with a different color. The second carbon, this one. This carbon is missing a bond, right? You have on the wedge, you have on the planes, so hydrogen will be on dash. And hydrogen is group number 4. For determining groups 1, 2, and 3, we have 1 and 1. 2 oxygens, 1 oxygen. So this side is group number 1. Carbon, carbon, oxygen, carbons. So this side is group 3 and this side is group 3, this side is group 4. Hydrogen is still in the back, so 1 to 2, 2 to 3 makes it R again. So both of the chiral carbons here are R. Another type of question and skill that you need to have in this part is how to draw a specific configuration. It's time to be fluent in how to draw a certain configuration like R or S. For example, working on drawing R, I'm working on page 5. Three-methylhexane. 3-methylhexane. You can go with either line bond structure or a skeletal structure. Let me put the line bond structure. Skeletal structure. 1, 2, 3, 4, 5, and 6. That's the hexane, right? And there is a methyl group on the third one. It's always easier to put hydrogen in the back and put methyl in the front. We need an R, okay? So this is group number 4. 1, 2, 3 carbons, 1, 2 carbons, 1 carbon. So this is 1, this is 2, this is 3. So we need an R, and hydrogen is already in the back. So rotation is going to be counterclockwise S. So this is not what we wanted. What is the fastest and shortest solution? Is to switch the location of hydrogen and CH3. So this time put CH3 in the back, hydrogen in the front. So you always start with hydrogen in the back and switch it if you have to. 4 and 3. So now the rotation is 1 to 2 to 3. It looks like S, but because hydrogen is in the front, this is the second situation, so it's actually R. So whenever the least prior group, group number 4, is in the front, we switch the letter of that rotation. We already talked about it. Situation number 2. That's the shortcut, huh? The next one, which has 2 chiral centers, we're talking about 3s, 6s, 6 isopropyl, 3 methyl decane. 3, I have to write it here, methyl decane. So in the longest chain we have how many carbons? 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. We have a group on 6, 1, 2, 3, 4, 5, and 6, and we have a group on the third carbon. Okay? The rotation should be S. So let's put hydrogen again in the back on both, and then we can fix it. And let's put the what is on the third carbon and methyl, and what is on the 6th carbon and isopropyl. Isopropyl, remember, it looked like a V shape. So and CH3 and CH3 here. So let's see if configuration with both S and S. For carbon number 3, this is the 4th group. This side is the first group, this side is the second group, and this side is the third group. Hydrogen is already in the back, rotation is counterclockwise, so 3s is correct. Good job. For carbon number 6, again we need to have an S configuration. Let's see. Hydrogen is the least prior group. This side carbon, 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 and you see all of them are carbon. Carbon connected to 2 carbons here, carbon is connected to this, and carbon is connected to the rest. So this is the first based on atomic number, and this is the second, and this is the third, right? So 1 to 2 to 3. Again, hydrogen is already in the back, the rotation is counterclockwise again, so this is S. So this is 3s, 6s. So get familiar with writing this way. Whenever there is more than one chiral center, we need to separate them with a comma, but they both come first in parentheses, and then we will write the rest of the molecule. So far, we just talked about the enantiomers, and up to this point, we know that physical properties of enantiomers, physical properties of enantiomers, the mirror images that are not superimposable, are same as each other. What are the physical properties like density, like melting point, and boiling point? They are the same for enantiomers, the compounds that are mirror images, just like our hands, but they're not superimposable. There is one difference between them that allow me to explain it in a few minutes. Okay, so the first type of stereoisomers, which were enantiomers, mirror images, non-superimposable. We learned everything about them, how to find the configuration of stereoisomers, and we also learned about enantiomers, that their physical properties are the same. Their melting point, their boiling point, and we're going to learn more about them. The second type of stereoisomers, so far, stereoisomers, we learned about enantiomers. The second one are called diastereomers. Diastereomers. The difference between enantiomers and diastereomers is that enantiomers were mirror images and not superimposable, right? Mirror images. Non-superimposable. Diastereomers are not mirror images, and they are non-superimposable as well. So that's the second type of stereoisomers we're going to determine, and determining RNS is the same as enantiomers for them. We normally study and see the diastereomers in biological molecules. Look at page 6 and look at these 4 molecules drawn for you. We normally dig the molecules with more than one chiral center, more than one stereogenic center. We show it as this. These are the 2 carbons are stereogenic. Okay? And I show you in a minute how to draw their, to determine how to determine RNS in them. This should have drawn it a little bit lower. Molecule A, molecule B. We needed to, okay, then write them smaller. Okay. I'm still used to the classroom whiteboards, obviously. And the last one, all right. So now the question is, there are a couple of questions asked from you. Any 2 which of the mirror images of both carbons are enantiomers? Yes. Which would be enantiomers amongst these A, B, C, D? Means we need to determine the mirror images. All the molecules, the mirror image of the other molecule. So to me, seems like A and C are enantiomers. Enantiomers, A and C. Anything else? How about B and D? Right? B and D. And which one of them are diastereomers? Means which one of them are not mirror images? Diastereomers, the ones that are not mirror images, I would say they are A and B, C and D. Correct? So that's the difference between diastereomers and enantiomers. How to determine a diastereomer is R or S if you put everything on the horizontal line on the wedge, they look like a bow tie, right? They are called Fischer configuration. So put all the horizontal groups on the bow tie. So now we said these two carbons are chiral, right? So we need to determine R and S. Hydrogen is the fourth group. We take care of this one first. That's the carbon number 1. Carbon number 2, I'm sorry, because 1, 2, 3, and 4. So we're not going to name the entire compound because we don't know how to. It contains more than one functional group. But let's just determine the configuration. Carbon number 2 has 4 as hydrogen. Between nitrogen and carbon, which one has a higher atomic number? Nitrogen, because it's element number 7. Carbon, 1 oxygen, COOH is COOH. 3 oxygens, so this is group number 2, and this is group number 3. Hydrogen is on wedge, is in the front, so whatever rotation we see, we have to flip it. The rotation looks like S, but it's actually R, correct? Because hydrogen is in the front. The next one, which carbon? Third one. This is carbon number 2, this is carbon number 3, carbon number 1, and carbon number 4. So hydrogen again is the least prior. Oxygen is the first priority because comparing to 3 carbons, oxygen has a higher atomic number. This side is carbon and carbon, carbon to another carbon, but the carbon just to hydrogens. So this is group number 2, group number 3. Now, hydrogen again is in the front, so whatever rotation we see, we have to switch it. 1 to 2 to 3 to, it looks like S, but again it is R. So this configuration is 2R, 3R. So we ignore half of the molecule and we just determine the configuration for 1 carbon and we go to the other carbon. Let's do it for this carbon, for this compound. Again, 2, 3. And this is the same for all of them. We're going to do it for all of them. 2 and 3. Okay? So this is carbon number 2. The same bow tie. Group number 4. Nitrogen is group number 1. This side and this side. This is group number 2. This is group number 3. Hydrogen is in the front. When you see S, it's actually R. For this carbon, hydrogen the fourth one, oxygen the first one, carbon, carbon, hydrogens another carbon. So group number 2, group number 3. Hydrogen is in the front, so whatever we see, we switch it. It looks like R, but it's actually S. For the third one, now you have a better idea of what we're doing. Bow ties, and priorities. 4, 1, 2, 3, the same as how I explained. Those are the same groups, so I'm not gonna take any more time. 1, 2, 2, 2, 3 looks like R, but hydrogen is in the front, so it's actually S. And the third carbon, group number 1, 2, 3, and 4, hydrogen is in the front again. So in these types of configurations, hydrogen is always in the front, so you need to use the second rule. So it looks like R, but it's actually S. Here, bow ties again. 4, 1, 2, 3. So it looks like R, but it's actually S. And bow tie. 1, 2, 3, and 4. It looks like S, but it's actually R. Now, I took time to determine all of these configurations to show you something. Didn't we say that enantiomers are A and C? A and C are A and C are enantiomer, right? What do you see in their configuration? RR changes to SS. So if you have enantiomer, means they're mirror images, right? And the mirror, everything is inverse, not inverse. Let's say it's flipped. So R is flipping to S. So for enantiomers, R changed to S, S changed to R. That's how you determine which one is enantiomer. So if you were given some compounds, all the R's change to S, all the S's change to R, so they're enantiomers. How about diastereomers, A and B? What do you see for A and B? R remain the same, but the second 2R remain the same. 2R, 3R changed to 3S. Didn't we say that diastereomers are not mirror images of each other? This is showing here. When you see a change in one of them, but the other one does not change, mean that they are diastereomers. It takes us to the last practice. You can do the previous practice based on what I worked on. Let's work on the last practice on page 6. It's asking you, without drawing the structure, decide if the following pair of compounds are enantiomers or diastereomers. Still page 6. 2R, 3S, hexane, 2 and 3 diol. And the second one is 2R, 3R, hexane, 2 and 3 diol. So we just briefly scanned the name to make sure we're talking about the same compound. But what we mean is here, you see the first one hasn't changed, but the second one has changed. Means they are not mirror images of each other, so they are diastereomers. Or we could have changed in this first one and then the second one doesn't change. The second one, let me eliminate the complete name. You already have it in your study guide, and the rest is, and this next one is 2S, 3S. So what do you see here? You see R in both of them changes to S, means they are mirror images, so they are enantiomers. So if both letters change, you will have enantiomer. If only one of the letters change, you have diastereomer. Look at C, 2R, 3S, 4R. This compound has 3 stereogenic center. And the second one is 2S, 3R, 4R. What has changed? The first one only, right? No, first one and the second one. But the last one hasn't changed. So they are again diastereomers. So watch out for these. These are good grade makers. I call them grade makers. So make sure you know it well. Work on these two videos. Make sure you know everything. We are going to finish this chapter with the third video about mesocompounds, racemic mixtures, and finishing the properties of enantiomers and diastereomers. The last thing before I finish this video is that about enantiomers, we said they have same physical properties like melting point and boiling point and density. About diastereomers, they have different physical properties. Like in real life, one of the diastereomers can be a medicine. A second diastereomer might be a poison or might be nothing, just a molecule without any specific medicine or real life properties. So that's what I wanted to tell you, the difference between diastereomers and enantiomers. We are going to work on the properties of diastereomers and enantiomers. Again, the last thing left is the rotation of polarized light after you are completely done with these two types of stereoisomers.